Okay, let's start. Probably let's do a quick recap. So in the last class, we started to look at SAR ADC, and we basically came up starting by noting that in a flash ADC, the main issue is we need so many comparators. So we decided to do this comparison or to do this conversion using a single comparator, and we saw that the most efficient way to do this is through binary search. So that gave rise to this negative feedback system, which is basically the SAR ADC. And we also saw how to subtract the input from different reference voltages using a bunch of capacitors. So the bottom line was, in a SAR ADC, we have the capacitors arranged in a binary weighted fashion like this. So for a 3-bit SAR, you had 4, 2, 1. And in the schemes that we have discussed, there is always one capacitor C that is connected to VRF all the time, right? And the simplest switching scheme we started off had this logic. At the kth step, you ground the kth capacitor to ground, and if the previous comparison output was 0, you flip the k minus 1th capacitor to VRF. This was the logic we started with, and then we extended it to a differential system also. And here there were two variants. One, we saw that we could provide the inputs, we could provide the reference voltage also in a truly differential fashion, right? So if the differential reference is some k VRF by 4, you feed it as plus VRF by 8 and minus VRF by 8 in the two halves. And basically this is what I gave you to solve in the mid-semester also, if you think you will get it. But we saw this was not this was not that efficient, especially because the differential reference we want is k VRF by 4, but in each half we are giving a reference of k VRF by 8. So for let me close this. What happened to this? Okay, yeah. So if to feed a differential reference of k VRF by 8, in each half we need a total capacitance of 8C. So that was taking up a lot of area. So we decided not to bother with this. And the reason we did a differential version was to keep the common mode of the plus and minus to be constant, right? But we decided we'll not worry about keeping the common mode constant. So that gave rise to this, wherein what we do is the following. If the input is greater than 0, we have to compare with positive references. So we do the switching only in the positive side. If we were to compare with negative references, we switch the capacitors in the negative side. That's all. And the same logic we follow as before, and that gives rise to the overall circuit like this. So again, the logic is same. The first you put the initial voltage of V in minus Vref, and then you disconnect the input. So these voltages will be at VIP, VIM. First you compare if it is greater than 0, less than 0. If it is greater than 0, you change in the positive side. Less than 0, do in the negative side. But in the logic that we have seen, we do two things. We ground the kth capacitor to ground, and if the previous comparison was 0, you go and flip the k minus 1th capacitor back to VRF. So we noted this was taking unnecessary power. So we tried to resolve this, and this eventually led to the monotonic switching scheme. So I'll just show the final result. So there, the only difference is this: we just do one thing in each step. In every step, if the previous comparison was 1, you ground the k capacitor in the positive half. If the previous comparison result was 0, you flip the capacitor, the kth capacitor to 0 in the negative half. That's all. So as you see, this logic itself is pretty simple. Just need to do one step, and this is more energy efficient, and also the logic is also pretty simple to implement. Okay. And this monotonic switching is what is very commonly used now also. So we'll continue from this point, and we'll see how to implement this logic, right? We know this is what we want, but how we are going to switch the capacitors to these reference voltages, that we will see today. So this is Let's start today. So in a SAR, first let's list out what are the operations we have to do sequentially, right? First, what we have to do in the ADC? We have to sample the input, and after sampling, what do we do in the SAR? In the SAR, what do we do next? We compare with the zeroth reference voltage, and then let us say if it's an n-bit SAR, how many times I'll have to do the comparison? We have to do it n times. So we have a total of n comparisons.
Is it always n?
Is it? Right? So totally we have, let's say, n plus 1 operations. Right? And let's say this is the clock available to us, sampling clock, let's say 0 and TS. So we have total time of TS to finish all the n plus 1 operations. So what would be the simplest thing to do? What is the time you might allocate for each operation? TS by n plus 1. So that seems like a simplest thing to do. And usually in the older times, the way this was done was as follows. To the ADC, you fed in a clock like this with a time period of TS by n plus 1. So if this is at a frequency Fs, this is running at a frequency n plus 1 times Fs. Okay. So if you want to have a SAR ADC operating at the rate Fs, the input clock to the ADC must be at least n times higher. Right? So then what you can do is you can say in the first clock period I'll do the first operation, second clock period I'll do the second operation, and so on. So this was done in the earlier times, and this is usually referred to now as the synchronous SAR. It is synchronous simply because each operation is done at specific time instance like this. At the first rising edge, let us say you do the first operation, second rising edge you do the second operation, the time instance are well defined. This is nice if you are looking at low speeds. So let us say I look at a 1 kHz ADC. If I want a 10 bits, I'll leave let's say 11 kHz of clock. This is okay. But let's say I want to have ADC of 100 MHz. The clock I should feed to the ADC is more than a gigahertz. So this becomes really difficult, and that is why SAR ADC was always used as a very low speed ADC in the olden times. But later people figured out, instead of actually feeding a high frequency clock, we can actually feed in this low frequency clock and do all the operations in an asynchronous manner. That is, here the time instants are well defined for each operation, right? So instead, let us say you do the first operation, detect when we finish the first operation is done, start the second operation automatically. You detect when the second operation is done, start the third operation automatically, and so on. So you do some kind of a self-timing within the ADC, then you don't need to provide a high frequency clock. So let's look at it in detail. So this is what is done now, and this is called asynchronous SAR. Again, there are different ways in which you can have this asynchronous logic. I'll just discuss one way in which you can do it, especially for monotonic switching. And the way this logic will be implemented will also depend on the way in which we are switching the capacitors. Okay. So let's list out what are the sequence of operations we have to do. So first, as we know, we have to sample. And once we sample, we compare the input with 0, right? That's a differential reference. We first simply do comparison. After that, in the monotonic switching, if the previous bit was 1, the kth capacitor in the positive side is flipped to ground. If the previous result was 0, the kth capacitor in the negative half is flipped to ground. And then what do? We keep repeating this continuously so that total of n comparisons is done. So wait for totally n times. This is the logic, right? So let's see how we can implement it. So first operation is sampling, as you know. So let us say I have a clock like this. Phi is sampling clock. So this time instant is, let us say, Ts. Let us say you can feed in a clock with a small duty cycle like this to your ADC, or even if the clock input is 50% duty cycle, you can generate a small pulse without any issues. Okay. So let us say this clock is there. We sample the input. Fine. The next step, what is the next step here? We have to compare with the differential reference 0. So let's say I have to fire the comparator. So let's say this is my comparator. Now remember that in all the comparators that we have seen, they are all clocked comparators. That is, when the clock to the comparator is high, the comparator regenerates, and when it is 0, what happens? We reset the output, right? So here, when do you think we can? When do you think the comparator can regenerate? Yeah, once phi s goes slow is when you can actually regenerate. So let us say I call the clock as phi reset. So basically here I am showing reset clock, that is, if this clock is high, the comparator is reset. If it is slow, it will regenerate. This flipped version, right? So now you know that during this phase is when it can regenerate. So what clock can be used as reset now? When can I reset it? I mean, I'm going to regenerate during this phase. So when can I reset the comparator? I can reset during this phase. Is that okay? When I'm sampling the input, the comparator is not used, I'll reset the comparator. Once I finish sampling, I'll regenerate. Right? So what can I mean, if I call the reset clock as phi reset, for now I can make it equal to phi s. Okay? Right? So great, now let us say the comparison starts once phi s goes slow, and let us say the first comparison is over here. Right? Now in our flow chart, we have to do this switching next, but before that we have to detect when the comparison is over. Right? We have sampled it, it's fine. We started the comparison, it is okay. But we have to detect when we have finished this comparison operation. Only then we can start the next operation, right? So how do you think we can detect when the comparator has finished decision? Sorry? Yeah, so how do you think we can implement? Let us say the outputs are D plus and D minus. When the comparator is reset, what can you say about the two outputs? They will be at VDD, so let's say both are at logic 1. When it has finished the comparison, it will be like this. So what is the simplest logic that you can think of that gives an output of 1 once the comparator has finished the comparison? XOR is fine, but NAND is also fine, anything. Simplest thing is NAND, right? XOR is also fine. So basically I will take these two guys, give it to an AND gate. I will generate a signal called valid. So this valid signal will go high once the first comparison is done, right? So let's say I will draw valid here. So let's say at this point comparator has finished the comparison. After a small delay, the valid will go high. Okay, great. So now we have detected when the first comparison is over. Now in principle we can start the next operation and start the next comparison, but remember that once we finish the first comparison, we have to store its output, right? Because the next time we fire the comparator, it's going to give the next bit. So we have to store the first bit we got. So how do I store a digital bit? You put a flip-flop, right? So simplest thing is to have a D flip-flop. So let's say I take only the positive output DP, give it to the D input. And remember, let us say I have a 3-bit SAR. The same comparator output, I'll have to give it to 3 different flip-flops, like this. So let us say this is the first bit D1, D2 and D3. Now, I mean, how will I differentiate which is D1, D2, D3? I have 3 different D flip-flops. The D input to all the 3 flip-flops are same. I should somehow give different clocks to these, right? So let's say I have clock phi 1 to this, right? So this phi 1 clock should go high once the first comparison is done, right? So the first comparison is done when the valid goes high for the first time. So we have to generate a clock, let us say phi 1, which goes high just after valid goes high. Similarly, the second time valid goes high, you have to get one more clock phi 2 that goes high when valid goes high for the second time. For getting the third bit, you have to generate clock phi 3, and this clock phi 3 should go high when valid goes high for the third time. Is that clear? Each time a valid signal goes high is when the comparator has made the decision. First time it goes high, you generate a clock phi 1 to get the first bit. Second time it goes high, you make one more clock go high to store the second bit, and so on. So one way to generate this clock phi 1 is you take D flip flop.
Valid itself, right?
Yeah, so we'll use a valid as a clock. Remember, see, once valid goes high is when this has to rise, right? So valid must be given as a clock to another D flip flop like this. So if I do this, I call it phi 1.
You can just give directly valid to the clock, right?
But remember that next time the comparator finishes, valid will again go high, right? So we'll come to that. This is fine now, okay? So the D input is always 1, but only when valid sees a rising edge is when phi 1 will go high, and then it will stay like that. That's all. Okay. So what you have to do first, once valid is generated, you have to generate this clock phi 1, and using that you go and store the data. So once the data is stored, we can do the rest of the operations. The next operation is this. If the output is 1, you connect the kth capacitor to ground in the positive side. If it is 0, you do it in the negative side. So I'll just draw only one capacitor. I'll show only the positive side for simplicity. So let us say this is the capacitor in the positive side. So I'll either connect this guy to Vref or to ground. And remember that I will connect this guy to ground if D1 is 1, right? So what can I give as a control to the clock?
D1.
Yeah, we can actually give D1 itself, but instead of giving D1, what we have to actually give is D1 times phi 1, simply because D1 is the output of a flip-flop that can have some value by default. Remember that the switching has to be done only after we finish the first comparison. So two things we have to take care. We have to check if the first comparison is done, and then we have to check the value of D1. Based on both these conditions when we have to switch the capacitor to ground, right? Because even otherwise, when phi 1 has not gone high, D1 can have some previous value, right? Previously, let us say D1 was high. Then we don't want this to. Yeah.
How do you ensure that phi 1 was 0 before?
That will come to it later. Yeah. Initially, when you start, we have to reset all. We'll come to that at the end of it. But let's say for now it starts with 0. So this will be D1 times phi 1. So when what will be the control for this guy? When it is not connected to ground, we have to connect it to Vref. So what should be the control? Bar of that. So what kind of switch I can use for this? I mean, this is you can get by AND, but I'm asking what switch I'll use for this switch. NMOS switch. So let's replace everything, and the gate will be given to D1 phi 1. So here what switch I'll use? PMOS. Vref is close to VDD, right? Remember. That's clear? No, this is connected to Vref, right? Vref is usually VDD, use a PMOS. So what will be given as the gate to the PMOS? The control to the switch is D1 phi 1 whole bar.
We give the bar of it.
We give the complement of it, which is D1 phi 1. So this is Vref. Clear? That's all. So similarly, we'll have the same structure in the negative side, and in the negative half, we have to flip the capacitor to ground when the output is 0. So what would be the control for that? Here we have to flip the capacitor to ground when phi 1 is high and when D1 is 1. In the negative half, we have to flip it when phi 1 is high and when D1 is 0. So what could be the control? Okay, so same will happen here also. the negative half, this how it will be. I'm not drawing it. Okay? So once you do this, you come here. So the sequence is this: once valid is generated, you create this clock phi 1. Using the clock phi 1, you save the data D1, and once D1 and phi 1 are available, you can switch the capacitor properly. Once this is done, the next step is go and repeat the comparison, right? So now we have to fire the comparator once again, but remember that comparator has already made a decision and one of the outputs is at 1, other is at 0. So to restart the comparator, what should I do? I have to reset the comparator once again. So what signal can I use for resetting the comparator here? Phi s we have already given, but phi s is 0 after this, right? So along with phi s, we have to give some other signal now for resetting. Which of the signals here can be used for? Valid can be used. I mean, think about it. What we have done, the first comparison is done. Valid has gone high. And after first comparison is done, we have to start the second comparison. So I can actually use valid itself. Okay. So I can actually give this as valid. Yes, valid is already high. That is why once the comparison is done, valid will be high. So you add valid to phi s. So what will happen is after a short delay, let us say after this delay, comparator will be reset. Is that okay? So let me actually draw the reset signal also. If I draw the reset signal, initially it was phi s. So now we are also adding the valid signal to phi s, and I will be adding the two signals using an OR gate, right? So after a short delay, so this is when valid goes high. After a small delay of the OR gate, the reset signal will go high. Is that okay? Once reset goes high, what will happen to the outputs of the comparators? Both will go to 1. What will happen to valid signal? Valid will come to 0, right? So valid will come to 0. Let us say after a short delay. Now remember, the same valid signal is given as the reset. So if valid comes to 0, after a short delay, even the reset signal will come to 0. Right? So this is the time at which, after a small delay, reset will also come to 0. Now reset has come to 0, which means comparator can start comparing once again. We have already flipped the capacitors, so the next input is ready. So the comparator will start the next comparison. So let us say at this point, next comparison is also done. So what will happen first? Valid will go high after the comparison is done. And once valid goes high, we have to generate the second clock phi 2, right? For that,
we have time to reset goes 1, right?
Which one?
If two things there.
Yeah, that's what the point is. You are going to add this guy and then give it. So there will be some delay, right? If that is not enough, we have to add more delay to the valid signal. His question is, we are once the valid goes high, we are immediately resetting it, but we should have enough time to generate these clock and switch these guys, right? So usually, because this valid is ORed with this phi s and then reset, there will be small delay, and even for resetting will take some time, right? Usually that time is enough. If that is not enough, we have to go and add more delay to the signal. Instead of using valid, you delay the valid signal and reset. Okay. So the second comparison is done. So we have to generate the second clock phi 2, and I will do it like this. Same clock I will give. So now phi 2 will go high when phi 1 is 1 and when we have a rising edge in valid. So this will go high only when the second time valid goes active. Okay. So similarly, I'll also finish it. The third clock also will generate it the same way. Right. So now phi 2 is generated. So you go and store the data, and then do this switching of the capacitor in the same manner. Okay. So now let's look at the time again. So valid is gone high. In a short while, let us say you do all these things. Now remember that the same valid signal is given as a reset for the comparator. So after a short delay, let us say reset goes high. Now reset goes high, both comparator outputs are at 1. What will happen? Both are at 1, so valid will go to 0. So valid will go to 0 after a short delay, which means the reset also will go to 0 after a short delay. Now we can fire the comparator the third time. So once, let us say at this point, the third comparison is also done, valid will go high again once again. So this time we'll generate the third clock, and let us say it's a 3-bit SAR, we are done. Ideally this is the end of it, but let us say you don't do anything beyond this. What will happen is this, right? See, if you look at it, we are using this valid and giving it as a reset, and this is continuously happening in a feedback, right? So what will happen is this. So even after the third comparison is done, remember valid has gone high and the same valid is given as a reset. So reset will go high after a short while. Once reset goes high, what will happen? Valid will come down. So since valid is given as reset, this will come down. So comparator will compare once again. The inputs have not changed, but it will compare once again. So once again valid will go high and this will keep repeating. But you don't want it to repeat after we finish the third comparison, right? Because it's unnecessarily we are firing the comparator. So once the third comparison is done, you better go and reset the comparator for all, right? That way the comparator will not be doing anything. The outputs will be at VDD. Okay. So I will not let this thing happen continuously.
If that happens, can we lose the data?
We will not lose the data, right? Because the input we are not changing. Right? Yeah. And these are the final data. Data will not change, but we are unnecessarily firing the comparator and wasting power, isn't it? So once the last comparison is done, in this case the third comparison, once the third comparison is done, we have to detect it and reset the comparator once and for all. So which signal here marks the end of the third comparison? 5.3. So I'll use 5.3 for resetting the comparator. Okay. So once 5.3 goes high, now my reset will also go high. Let's say after a short delay, reset will go high. Once reset goes high, what will happen to valid? Valid will come 0 and then it will be like this, that's all. Right? But one last thing, this is something he pointed out in the beginning. So we started off by assuming all the 3 clocks 5.1, 5.2, 5.3 are 0 during the sampling phase, right? But here at the end of the conversion, they are all at 1. Note here. So we have to make sure that these 3 guys start at 0 during the sampling phase. So how can I bring the outputs to 0? Yes? 5S ka what do you have to do?
Like when the next time the sampling phase is
Correct.
on, then every clock will happen.
Exactly. So how do I do that? That's what you have to do in words. You use that 5S as a reset for these flip flops. Okay. So let's say this is the reset. I'll use 5S as the reset. Is that okay? If you do this, it will all be fine. So at the end of this, after 5S is gone, it will be 0 like this. So this is one way in which you can do this in an asynchronous manner. Now you see that you don't do each operation at fixed time instance, right? If let us say a comparator for some input, let us say comparator is taking a short time to regenerate. So the valid will come high very fast. You can start the next operation quickly. If let us say for some signal, comparator is taking long time to regenerate, you wait for that much time and then do the next operation. So it is not happening at fixed instance, it is very flexible and it is sort of self-timed. Okay. So if I had to draw the full thing properly, So we'll have it like this. So let us say I draw only the MSB capacitor. So this is the MSB cap. I connect this to Vref for ground. So let us say Vref. So here it was D1 times phi 1, D1 times phi 1. I have all the other caps. And in the switching scheme that we have discussed, there is one capacitor C that is always connected to Vref. So I have the same in the negative side also. So this is always connected to Vref, but all the other capacitors you connected to Vref for ground. So this will be D1 bar times phi 1. So this is the negative side. These two actually go to the comparator. And remember that we also have to sample the input, right? So we should have a switch here. And what should be the control for the sampling switch? Phi S. This is, let's say, Vi plus and Vi minus. Yeah, so you can either use a bootstrap switch here, or if you don't want a lot of linearity, you can use a CMOS switch. Either of them will work. So this is the comparator. Now we have to take the comparator outputs, generate the valid signal. Now the sequence is this, right? So first the valid signal is generated. So next you generate the clocks phi 1, phi 2, phi 3. Use those clocks to save the data D1, D2, D3, and once the data is stored, you go and switch the capacitor. So you generate the clocks that will need only a bunch of chain of flip-flops like this. So this is always 1 D. The clock is the valid signal. So this is phi 1, phi 2, and the last clock is phi n. And remember, all these guys must be reset when we are sampling. So the reset is phi s. And these clocks must be used for saving the data. And for saving the data, we are going to use another bunch of flip-flops. Let us say this is the plus input of the comparator. That is given like this. So this will be clock phi 1, this will be phi n. This will give all the data D1 to Dn. So one last thing is the reset for the comparator. Now we reset the comparator when we sample it, or when the valid is high, and when the nth clock is high. So we need a 3-input OR gate. So phi s, valid, and phi n. So this will generate the reset signal. So this is the overall thing, and this is one way in which you can have the asynchronous logic. So as you can clearly see here, right, whatever I have drawn in blue, right, so this is basically an OR gate, a bunch of flip-flops, an AND gate, and even this guy, the switches here, does it resemble of anything? Does it resemble you something?
Like switch only.
The two switches, if you think about it, I have a PMOS and an NMOS transistor. The drain of the PMOS is connected to the drain of the NMOS. Source is connected to VDD, this is connected to ground. Gates are same. What is this? CMOS inverter. These the two switches we have is essentially a CMOS inverter, right? So everything that I have drawn here in blue, it's a purely digital block, right? So you can actually make a SAR ADC using almost only digital blocks, right?
Comparator is
Only comparator is there, but of course even comparator you can think of it as cross-coupled inverters, right? So basically these ADCs in mixed signal design should not only be good in having a good knowledge in analog circuits, should also be fluent in making digital circuits, right? The switches we have, that's what I'm saying, right? In these mixed signal you can have both. In this SAR ADC in particular, it is more digital. Okay, and this actually, I mean, having a fluency in digital circuits is important here, especially because if you think about the SAR ADC, right, the idea of SAR ADC was known for a very, very long time. But for a long time, we were doing this SAR ADC in a synchronous fashion like this. So you always had to feed a high frequency clock. So it was always built as a low speed ADC. But it was only later people figured out you can do an asynchronous SAR like this, and this is actually not very old. This was done in the late 2000s, I think 2005 or 6. Done by Mike Chen, who's now a professor at USC. So only after asynchronous SAR was introduced, there was a renewed interest in SAR ADCs, and there is a whole bunch of work done in SAR. And after this asynchronous business has come, SAR has been used in all high-speed applications. Even the time-interleaved ADCs we saw in this wireline communications and serial links, they all interleave SAR ADCs to get the giga samples per second ADC. So, and I mean, even if you think about it, the boundary between analog and digital, it's now very blurry, right? Of course, you have purely digital circuits when you go to microprocessor, CPU architecture side. You also have purely analog circuits, but a lot of powerful and interesting stuff happen in this between region, right, where you have mixed signal circuits like this. And it's pretty nice because if you have a problem here, you can solve it either from analog, or you can solve it using digital, or you can use a combination. I mean, it's like you being the middle child, right? You can get help from both your elder brother or your younger brother or sister, but it can also backfire, right? You'll have problems from both ends also. So now you have to tackle issues from both analog side and digital side, right? Great. So yeah, I mean, so this is basically almost digital thing. So it has only dynamic power consumption. It scales easily. So all the advantages you see in the first paragraph of a digital IC textbook will all be valid for a SAR ADC also.